Hi everyone, I'm Shantan and today I'm going to talk about over-the-air assisted federated learning with timing delays, convergence and testing accuracy. This is an extended talk of our presentation in International Communication Conference 2026. So first I will give you a brief description of what is over-the-air federated learning. So the motivation is you have several spatially separated nodes and uh, you have to train a common machine learning model at a central node called the parameter server using the local data of the device. But there is only one constraint that you cannot transmit the data directly from any of the devices to the server. So one classical approach is federated stochastic gradient descent, or in abbreviation we call it FED-SGD. In this technique, it is an iterative approach, and in each iteration what happens is as follows. A device, suppose device K, computes something called a local gradient, which I term as Gk of n. And the local gradient is really, it computes the gradient of the loss function on the global model and the data available to that device K. And it uses a batch of data points across all the data because it's computationally expensive to compute this gradient on the entire data point. Second, then the device K sends its gradient, local gradient to the parameter server, and the parameter server updates the global model as follows. The updated global model in the next iteration is the old global model in the previous iteration, minus there is some scaling, which depends on something called a learning rate, and there is a summation of the local gradients from all the devices. Now, so we clearly need an aggregation of the local gradients at the parameter server in order to compute this step. And how we can do it? There are several approaches. One approach is called the over-the-air computation. So in this approach, all the devices transmit their local gradients on a shared time frequency resource. That means just send over the same carrier frequency in a time synchronized manner. And in this way, if you do, let's see this figure. Suppose this is device 1, it is sending a signal that constitutes of its local gradient. And this is a device K, which has a similar signal. And if they transmit in a time synchronized fashion, then the channel will do the sum for you. So because of the interfered signal, we use that interfered signal and then we scale it up by a receiver scaling. Obviously, noise gets added at the receiver, and then we pass it to a match filter and sampler. And the sample outputs we use to learn the global model as this suggests. So in OTA-FL, instead of the summation of the local gradients, we proxy it using this received samples from the match filter outputs. Now, there are practical issues to this setup. First practical issue is that I told you that that devices has to be time synchronized, but in reality, the devices can be time misaligned. There can be several reasons. The devices can be at different distances. Then when the parameter server receives the individual local gradients, they are misaligned in their time domain. As you can see in this figure, the device 1 is misaligned by tau 1, the device 2 is misaligned by tau 2, and the device K is misaligned by tau K. And there can be other reason as well. The local oscillators may be in desync, and that can also cause this kind of misalignment. The second issue is that the channel, you need to estimate the channel at the devices and the parameter server. And this the channel estimation can be imperfect. For this talk, we'll be only focusing on timing misalignment at the parameter server. We have a subsequent paper on how to handle the imperfect channel state information. Okay, let's come to the main point of the paper. So several people have looked into this system of misaligned federated learning system, and they use a match filter called a whitened match filtering and sampling scheme. In this match filter, what happens is that you use k number of match filter. K is the number of devices, so that many number of match filters you need. Each of the match filter has its duration is adapted to the timing delay differences. So for example, if the delays are like tau 1, tau 2 to tau k, the first match filter timing will be tau 2 minus tau k. So it will be here. And then similarly, you have k such match filters, and then you take the samples at the end of the delays, like tau 1 after tau 2 after tau k. So you get k such symbols, And for the entire duration of the gradient transmission, because the gradients are m dimensionals, you will get a total sample of the order of k into m. So it's a large number of samples, and then actually what you need is this Rn, which is m dimensional vector. And to get this m dimensional vector, you need to use an estimator. An optimal estimator will be a maximum likelihood estimator, which has a complexity of k square m square log of km, which is huge amount of complexity considering the case that m can be very large in millions. So this is one approach, and using this Rn, people have tried to establish an OTA-FL system, but we have looked into something simpler. What if we use a conventional match filtering scheme which does not know the delays? Here is the picture of the conventional match filtering schemes, where what we do is that after each symbol duration, that is t, capital T, this is the match filter duration, and we take the samples at the end of this duration, and that's how we get m number of samples, and we use these samples as the proxy of Rn. And the good thing about CMFS, or the conventional match filtering scheme, is that it's delay agnostic. You don't need to know the delays a priori at the parameter server in order to design this match filter, and it also incurs lower receiver complexity because this whole maximum likelihood estimator is not required anymore. So let's look at how good or bad is a CMFS based over the air computation setup, which is which is misaligned in timing. The devices are misaligned in their timing delays. So we have found out that the received signal vector at the parameter server, the samples, which is of dimension m, is like this. So it has a scaling of the receiver, then there is a sum over the channel. This is the channel gains. This is the transmit power of each of the individual devices, and there exists a matrix. This is a 1 minus tau k is the scaling, and this is the identity matrix, and then you have a tau k by t into a lowership matrix J, then into the local gradients, plus there will be some noise, scaled noise due to the receiver. Now what this really tells us is that if you take the suppose 10th component of your received signal vector, the 10th component will depend on the 10th component of the local gradient and also the 9th component of the local gradient because of the overlap. So we now analyze such a system. How does really the system performance, that is either in theoretically we capture the optimality global loss function computed over that particular iteration of global model, and this is really the minimum amount of loss we can achieve in reality. This may not be known in practice, but there is always a lower bound. And this optimality gap, really what it says is that you measure the distance, how far you from the optimal value, you average over the batch selections because each device has a batch to select in each iteration, and the receiver noises, and you condition on the channel gains up to the nth iteration, up to that iteration. So this is the optimality gap at the n plus 1th iteration, and this is really the key result of our paper. This states that if our learning rate, that is eta, satisfies this inequality, certain condition, then the optimality gap at the n plus 1th iteration follows this following recursive relation, where it decreases by a contraction factor in each iteration called the alpha n, and there exists an additive residual error. So let's look at how these contraction factors and residual errors evolve and how they depend on the timing delays and the number of model dimensions. So for the contraction factor, it's a quadratic. It's a quadratic on eta. Eta is our learning rate, and also the contribution of the delays really come here. So what happens if you one more thing, there is a theta m term here. If you look at the theta m term, the theta m is nothing but pi by 2 into m plus 1. And if m is really large, this theta m shrinks down to 0. And if this theta m shrinks down to 0, then cos theta m goes to 1. So, and you get 1 minus 2 tau k by t. And as tau k's increase, as the delays increase, this term decreases. And if this term decreases, there is a minus sign in forward. So in effect, totally the contraction factor increases as the delays decrease. So you contract less in each iteration as your delays increase. The second point is the residual error. In the residual error, the effect of delay is captured in this epsilon k. And if you see, I have written here epsilon k, it's a function of delays and a theta m. And for large models, the sine theta m shrinks down to 0, and this epsilon k has become unity. And therefore, for large models, the residual error is insensitive of the timing delays. It does not matter. These are the two key results that we come across of the CMFS-based system. Now, let's look at how in practice for a synthetic data set called C410, which consists of 10 different classes of images, the results, how are the results? So, let me go through the simulation setup first. So, we have used an convolutional neural net, which is called standard ResNet 18 model. It has 11.2 million parameters. We have taken 10 devices, and there are two settings we have done of data partitioning, because what we do is that we partition this whole C410 data set, all the training part of the C410 data set, into 10 devices, across 10 devices. And the partitioning scheme we use is called using a Dirichlet multinomial distribution, and this number in the parenthesis is the concentration parameter of this distribution. It really determines how much of a class participates, how much of a class is present for a particular device. If this number decreases, then you will see that one class is dominating for one device and another class is dominating for another device. If it is going towards 1, then you will see that more or less all the devices have similar participation of data points from each of the devices. So we call this Dirichlet one as the homogeneous distributed data partitioning, and 0.5 is heterogeneous data partitioning for these two settings. And the delays are as follows. So this is your symbol duration 0 to capital T, and now you set a tau max, which I set it to some arbitrary value x, which is in between 0 to T, and the delays of each devices are 0.1 of x. The first device will be 0 because the match filter can cancel out the first delay always. So first device delay is 0, second device is 0.1 of x, third device is 0.2 of x, and similarly the 10th device will be 0.9 of x. So as your x slides, as your x increases, all of the delays will also increase. So therefore, whenever tau max increases, all of the delays will increase. Now let's look at the simulation plots. So what I plotted here in the left side of the plot, the truncated channel inversion, this is a particular channel inversion scheme in which the devices transmit invert their channels, but if they are really in deep fade such that overall transmit power of the device is not sufficient to invert the channel, they will shut down. In this case, I have plotted in blue is WMFS, in blue solid line, the first line. These two ellipses are one for homogeneous and one for heterogeneous. Let's just first look at the homogeneous setting first. So the top line is WMFS. WMFS is the whitened match filtering approach. It is certainly better than the second line, which is dotted plus. This is the CMFS, and this is for a tau max of 0.5. That means 0.5 microseconds, and the symbol duration is 1 microsecond. Therefore, 50%, your tau max is 50% of the symbol duration. So your delays are there, but they are not too severe. For this case, we see that the WMFS is certainly better in this case. But as the delays increase from 0.5 microsecond, tau max 0.5 microsecond to 1 microsecond, we see there is a decrease in testing accuracy, and this is bound to happen because your contraction factor decreases, as I've shown, as delays increase. And if you contract less, you will eventually go to a loss which is worse than what you can achieve in a low delay scenario, and therefore that affects your testing accuracy inversely. And also we see that for heterogeneous partitioning, when there are a lot of heterogeneity across devices in terms of the data partitioning, you will see that the delays affect first of all they affect more, and the testing accuracy naturally degrades. Second, there is an interesting result, that's why I'm showing it here, is follow scale channel inversion, where the devices, all of them invert their channel. Yes, they also follow the peak power constraint for each of the devices, But if you know, the channel inversion is like some multiplication, some a by mod of h square, a by channel power gain. You can decrease that a down so that all of the devices will transmit at lower powers, but eventually all of them will transmit. You can ensure that. That is called a scale channel inversion. In this case, one interesting thing I will show that in fact, if for a high delay scenario, your whitened match filtering scheme, that is tau max equal to 1 microsecond, is worse than your conventional match filtering scheme. So the key takeaways are as follows. As tau max increases, the slower contraction leads to a lower testing accuracy and a higher loss. And CMFS is really close to WMFS despite its lower complexity and delay agnostic design.